see. After the first session, which is mostly about introduction of coordination compounds, now let's go through identifying the IUPAC names. There are basic rules that are followed in IUPAC name. First thing that is to be taken care is cation should be written first, then followed by the anion part of the complex. While entering into the coordination sphere, always we have to write the ligand name first. And ligand name should be always in the alphabetical order. Common name of metal must be used in case if the complex part is cationic or neutral. Usually a Latin name which is a common name which is given is what is to be used. Latin name must be used in case if negative part of the complex is present, and it should always be ending with 8. For example, tin, lead, silver, gold, nickel, aluminum. These are its common name. While if you write it in this Latin name, especially when you have an anionic complex form, then it is stannate, plumbate, argentate, aurate, nickelate, and aluminate. These are the names that is to be used. Okay. Now let's go one by one. What are the names? Using the examples, I'll explain each and every rule here. Please check first case. First case is we have a platinum and chlorine outside. So first, make sure that if the complex is being broken into two pieces here, two with 4 plus and 2 with 4 minus plus 4 Cl minus. If this is how it has been broken, okay. You can notice that now it is a cationic complex. This is a cationic complex. And then try to also figure out what is the oxidation state of platinum. If X is the oxidation state of platinum, then ethylene ethylene diamine has zero oxidation state. Zero charge on it. Ammonia has zero charge on it. 2 times water has zero charge on it. Overall, we have plus 4. So, which clearly shows that X is equal to plus 4, which is the oxidation state of platinum. Okay. Now, using that, now you have to write the name. So, check out. First, notice alphabetically what will come first. This comes with ethylene E, amine AN, aqua AQ. So alphabetically, amine should come first. So that is the first thing you will write. So which is diamine. Amine will always be double M. And then we have diaqua, AQA, aqua. Okay. After that, we have ethylene diamine. So we have ethylene diamine, only single M. And next, we continue with the metal name, which is platinum. Why platinum? Because it is a common name, as it is a positive complex. And then write the oxidation state in bracket with a stock notation or Roman notation. Then give a space and mention chloride. Do not write it as tetrachloride because the oxidation state will take care of how many chlorides are outside. So it is never recommended to again write that. So this is the complete name: diamine, diaqua, ethylene, diamine, platinum, 4 chloride. Okay. So I hope all of you have written that. Please check. Now notice the second one. Second one we have 3K plus FeCN6 3 minus. Okay. 3K plus and FeCN3 3 minus. Now in this case, what do we have? It is an anionic complex. If it is an anionic complex, what will be the name? Always the cationic part should be written first, followed by the anion. So first we write that, which makes it potassium, then space. And now enter into the complex where ligand should be written first, which makes it hexacyanido or simply cyano. Both are fine. then it will become ferrate. That is the Latin name of iron, which is ferrate. Notice the oxidation state, x plus 6 times of minus 1 overall equal to minus 3, which makes x is equal to plus 3. So you have to mention the oxidation state as plus 3. So this becomes the complete name. I hope all of you got that. Okay. So this is how we need to figure out what is the name. Any doubt there? Please check. Finished? See the next one, everybody. Notice what will be the name of the next one. See. Again, if you split into ions, you will get this as 3K plus CrOX thrice overall 3 minus. Again, it is an anionic complex. Since it is an anionic complex, you will first write the positive part, which is potassium, then space. Enter inside that, you will get this is oxalate. So we have trioxalate. Trioxalato. Oxalate will become ato. Trioxalato. And this is chromate because it is an Latin name as well as anionic complex. So it should always end with 8. And then the oxidation state is plus 3 in this case. Done. Simple case. Please check. Clear with that? Next one. If it splits into ions, because this is a neutral ion, as there is nothing outside, it has zero oxidation state. You will directly write the name of the ligands, starting with cyanido, Cy, chlorido, Ch, okay, and aqua, Aq. So that makes it, di aqua, diaqua, dichlorido, dicyano, nickel, only nickel, because zero oxidation state makes it neutral. So when it is neutral, you should only represent their uh, common name. So now, using that common name, what is the oxidation state it has now? So x minus 2 plus 0 overall equal to 0. So that makes it plus 4 oxidation state. So like this. So this is the oxidation state. Okay. See the next one. If this complex splits into ions, it will become 2Na plus SnOH4 2 minus. So it is an anionic complex, and we have sodium. First, we have to write it as sodium, which is the cationic part, then space. Then we have tetra, tetrahydroxo, tetrahydroxo. Sn is stannate, oxidation state. Now notice the oxidation state here. So we have x minus 4 equal to minus 2, which makes it plus 2. So we would represent this as plus 2 here. The same goes with lithium aluminum hydride. The name will be simply lithium space then tetra hydrido hydrido aluminate oxidation state plus 3. So please do check. I hope you all able to write that. Okay. See the next one. Oxidation state wise, this is Na plus BH4 minus anionic complex. Oxidation state of boron is plus 3. So that makes it sodium. First we'll write it as sodium, then space tetra, tetrahydrido, tetrahydrido, boron. Okay. Borate, sorry, not boron. Borate, oxidation state as plus 3. Nickel DMG has 0 oxidation state. Nickel, if the oxidation state is X plus 2 times of DMG will possess minus 1 charge, overall equal to 0. So this is equal to plus 2 oxidation state. So now this is a problem. Notice if you write this as di and this is dimethyl dimethyl glyoxymeto glyoxymeto, then nickel oxidation state plus 2. Now this becomes wrong here. So this is not a correct way of representation. Why? If an organic molecule already has di, tri, or number mentioned in it, then again you will not represent that with the same way of numbering. Okay, same format of numbering. Instead, we use a new format of numbering, that is Greek numbering. So in the Greek numbering, normally if you have 2, you write it as bis. If you have 3 of the units, you write it as tris. 4, it is tetrakis. 5, it is pentakis. So this is how all the representation should go. Hence, now what is the name that will be suggested here is bis. Bis. Okay, that itself represent there are 2 of them. Then put it in bracket. Write the name now. Dimethyl glyoxymeto. Glyoxymeto. Then nickel 2. That's it. This will become the name now. So if you understood, when you have already di, tri, or any of the numbering present, you cannot represent with the same type of numbering again, not utilize that Latin naming numbering. Instead, you use the Greek numbering. Please let me know if anybody has a doubt here. I can discuss that. Done. Right, next one. Check out the next case. This one. K3. If you split this, it will become 3K plus cobalt En twice, OH twice, and Cl2. Overall charge is 3 minus. So which makes it first write down potassium, then leave space. Check out the oxidation state. This plus 2 times of 0 plus 2 times of minus 1 plus 2 times of minus 1 overall equal to minus 3. So X is equal to plus 1. Okay. So potassium, then we have to write alphabetically. This will become hydroxo HY. Got it. So this is ethylene E and this is chlorine C. So it is the chlorine which we have to write first. So therefore we write it as dichloro. Okay, dichloro. Then bis ethylene, ethylene diamine, ethylene diamine. Then dihydroxo. One second. Sorry, check out. So then we have diethylene, bis ethylene diamine, then dihydroxo, and then this will be cobaltate because it is an anion. You have to write it as state, and then oxidation state 1. Okay, so this will be the complete name. Everybody, please check that. All good. See the next one. Next one is Hg cobalt SnCN4. So if you split this, it will become Hg2 plus cobalt SCN4 2 minus. So oxidation state of cobalt is +2. Okay. So then, right. So notice that we have uh, mercury. We write this as mercury only. Then mention the oxidation state 2. Then we will leave some space. After that, there are 4 SCN. So it is tetrathiocyanato. Okay. Cyanide, this is cyanato. Tetrathiocyanato. Got it? Uh, cobalt, cobalt 8. Cobalt 8. The oxidation state is +2 here. So this is how you leave it. Please do check. Right. Next, NiCO4. This is a neutral complex. It has zero oxidation state. So we will write this simply as tetracarbonyl. Okay. Nickel oxidation state is 0. That's it. Simple. Okay. Next one. This is very interesting one, everybody. See, if both positive part and negative part, both of them are complexes, which means one should have an equal positive charge and the other one should have equal negative charge. Magnitude should be same for both of them. It could be either +1 -1, +2 -2, +3 -3, and so on. The general oxidation state of zinc is +2, which means if this complex is +2, the other complex form has to be -2. Okay. And see if that is justified in both the cases, which in this case is correct because zinc NH3 4 times +2 will keep the oxidation state or primary valency here as +2, while zinc CN 4 times minus 2 here will also keep the oxidation state as plus 2. So which is correct. So that means the oxidation state what they should possess on that is a common oxidation state, which is plus 2 and minus 2. So now how do we write down that? We'll write as if you're writing the anionic cationic part first and then the anionic part first. In the cationic part within the complex we have tetraamine, A-double-M-I-N-E, tetraamine, zinc, okay, with plus 2 oxidation state. Then space, we will have tetracyano, tetracyano or cyanido. You can write any of them. Then tetracyano, zincate 2, tetracyano, zincate 2. Okay. Clear everybody? This is how we need to use it. Please do check 9, 10, 11, 12. If any problem you have, you can ask me now. Done. I'll take it as a yes. We'll go to the next question. Same type we have. If you have nickel, how do we write down the name? So here, nickel can have plus 4 minus 4, but that changes the oxidation state. So to keep it common oxidation state, the best possibility is plus 3 and minus 3. Okay. Hence the name here this will be hexaamine, A-double-M-N-E, amine, hexaamine, nickel, hexaamine nickel. Okay. With plus 3 oxidation state, space, then hexachloronickelate, hexachloronickelate plus 3 oxidation state. Okay. So this makes more sense. You can write chloro or chlorido. A better thing is to write chlorido. Okay. Given the preference, always chlorido is written. But if chlorido is not mentioned in an option in a question, then go for chloro. Okay. Now this one is very interesting again. This is a complex where you have something called bridged ligands. These are bridge ligands. So when it comes to bridge ligands, how do we read it? Alphabetically, this will be C and this will be hydroxo. So that should be represented first, which makes it mu chlorido, then another mu hydroxo, right? Thereafter, you notice that this part on the left and this part on the right is exactly same, which means this entire thing can be written as complete one form as bis. So now I can write it as bis. So bis chloro, then chloro. After that we have triphenyl, triphenyl phosphine, which is the ligand name. Okay, chloro triphenyl phosphine and platinum, platinum. Okay, up to this is a common factor. So platinum has what oxidation state? Plus 2 oxidation state and close the bracket. Let me show you how to find the oxidation state also. There are two platinum 2x plus there are three chlorines, each one minus 1 charge. Plus there is one hydroxide which is minus 1 and PPH3 is 0 oxidation state. So overall 0. So that makes it 2x is equal to plus 4 and x is equal to plus 2. So that's how you'll get plus 2 as the oxidation state. So I suppose this part is clear. So this is how you can get, oxidation state as well as the complete name of complex which has bridged compounds or bridge ligands. Again check 11 to 13. See the next one. Another complex form, same type. This is NH2 NH2. So you can write it as mu comma mu diamine. Okay. Now this is amido. Please remember that this is not amine. It is not complete NH3. It is NH2 minus. So this is amide. So diamido. Mu comma mu diamido. Then we have bis. In bis we have tetraamine. This is complete amine. A double M. Double M I N E. Tetraamine. And cobalt. Cobalt with oxidation state as +2. Right. Close the bracket. Okay. Now space. Then you put it as a space, and outside you have to represent it as chloride. Okay. Again, how did I get the oxidation state? Simple. You can check it out. There are two cobalts plus there are two amido groups. So which means both will have -1 charge, right? And overall is +4 charge. So 2x is equal to 6. So x is equal to 3. X is equal to 3. So sorry, not 2, it is 3. Oxidation state is 3. Clear? This is about 14th one. Check out the 15th one. CuH2O4 dot SO4H2O. If you have it like this, we simply do not write as sulfate or some water molecule here. We usually write it this way. Okay. Tetra aqua, AQA, aqua. And then we have copper 2. And space, we have sulfate, correct? Monohydrate. We write this as monohydrate. If it is only one, it is monohydrate. If it is two, you will write it as dihydrate. This time you will mention how many water molecules are outside. Okay, clear? So I guess these 15 cases are understood, everyone. So this is how much variety you would get to write the IUPAC names. Okay, I have uploaded the questions based on IUPAC names completely. I mean, list of DPPs you will find out where first sheet is only about IUPAC and so on. Okay, different uh, subtopics you would notice there. Next. Now come to the next part of the topic, which is about Warner's theory of complexes. As per as per Warner's theory of complexes, got it? Our objective mainly is to designate how the complexes must look like. Now, generally, based on the NMR spectrography, how much number of chlorines are present, ammonia is present, how much cobalt is present, all together are represented this way. And this one is an old representation. But then comes the new representation, which is what Warner has proposed, that if this is how the molecule is, I mean, if this is the total content of the molecule, probably how it exists in a complex form is like this. That is cobalt, and the neutral complexes or the neutral ligands will always be the one which will get associated first. So 5 ammonia, and then we will have one chloride inside and two chlorine outside. Okay. Now you might say, sir, there are various permutations that way. Why can't I say simply put 4 ammonia, 3 chlorines out, and one more ammonia out? Or here I can write 2 ammonia here, 2 ammonia outside, or 3 ammonia outside like this here, because we have 3 here like this, or 5 here like this. Got it? Why can't have all these cases? Okay, why do we have to only go for this, only for this one? Now that's what we need to understand. As per Warner's theory, a complex of this kind can only exhibit two forms of coordination numbers. Either it could be 4 or it could be 6. Usually metals do not have multiple coordination, I mean wide variety of coordination numbers. So cobalt generally make an 6 ligand complex when you have sufficient number of ammonia molecules or sufficient number of neutral molecules. Since there are five, I just need to borrow one more. So that can be borrowed from one chlorine and complete the coordination number as six. And the rest of the chlorines, any charge answer present, they will always remain outside the complex. So this was the idea Warner's theory suggests. So remember that only two type of complexes, six ligands or four ligands. Priority is always about six ligands as compared to that of four ligands. Complexes with the neutral ligands are more favorable. That means ammonia will be more favorable to make a ligand connection with metals. So notice this one. If the example is given this way, that we need to represent this molecular weights into complex form. So how do I write that? So cobalt with H2O6 and close the bracket, and then we have three chlorines. Here, chromium with 4 ammonia and 2 Br2 and 1 Br outside. So that is one representation. Here, iron with H2O4 and 2 Cl2 and 1 Cl outside. This is one representation. Iron with 4 ammonia Br2. This is one representation. See, somehow I'm trying to fulfill the coordination number 6 inside the complexes. Zinc. Now, this is interesting. No matter how much you combine, the number of neutral molecules and the anions together are not coming out to be 6. Only in such cases, there must be 4 ligand complex nature. So, chlorine. This is 4 ligands, and then 1 Cl will be out. So, this is how the complex representations will be. All good. Now, what is all the basic properties which a complex will have? That depends upon how you represent. For example, if you have COCl3.6H2O, we just learned that how to represent it. That is cobalt H2O 6 times, and there are three chlorines outside. Electrolytic ratio is, which means what will be the ratio of these two? That will be, if you split them, it looks like cobalt H2O 6 overall 3 plus and 3 Cl minus. So there is one cation to three anions. So that is called the electrolytic ratio. So one cation versus three anions. Van 't Hoff factor. Van 't Hoff factor is about how many number of ions one molecule is splitting into. So if I take this one molecule, it is splitting into four ions, right? Three chlorides and one this complex. So there are four ions you will notice. So Van 't Hoff factor is 4. Primary valency is the oxidation state of central atom. So central atom oxidation state, you can clearly notice that in this case is +3. Secondary valency is the coordination number. For cobalt, you can see there are 6 water molecules, so coordination number is 6. So how do we represent the structure also? Check out. We have cobalt here, and then we have 6 water molecules. 6 water molecules implies 6 connections like this. So OH2, 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 and OH2. Okay, with 6 water molecules here, then you have three chlorines which are ionically bonded, right? Complex inside and outside will always have ionic bonded. So since it is ionically bonded, you will always have to represent ionic bonds with this dotted form. So there are three chlorides ionically bonded. So we will have Cl, Cl, and Cl. Okay. So this is a way to represent the structure. Please do notice everybody what is a Warner's theory and how to represent the structure. Quick. So check out PV here represents primary valency, SV represents secondary valency. Primary valency is the oxidation state of central metal atom. Secondary valency represent the coordination number of the ligand connections. And next. So if a complex is given like this, and I need to figure out this particular part of it, got it? That is, what would be its uh, electrolytic ratio? What is the Van 't Hoff factor, PV, SV, and structure? So let's look one by one. So this complex represents that chromium must have 4 4 ammonia, and 2 chlorines inside. That comprises of 6 ligands. The ratio here is not defined because it's a neutral ligand, so it does not have any charge. Van 't Hoff factor is only 1 because this is not going to split into any multiple ions. Then the oxidation state here is +2, secondary valency is 6. Okay. Structure, if you notice, we have chromium with 6 ligands here this way, out of which 4 of them are ammonia, NH3, 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 and then we have 2 chlorines here. Now remember one thing, chlorine is also responsible for generating the secondary valency, because if the uh, ligands have charge on it, they will be a part of primary valency also. That's why whenever you have a charged ligand inside the complex, you have to represent the dotted form also along with it. Got it? This is how you need to represent. So this is a representation of the structure. Okay. Same thing. Notice the next question here. So we have cobalt, we have NH3 6 times, then we have Br. So the electrolytic ratio is 1 is to 1. Van 't Hoff factor is 2 because these ions will split into two parts. Primary valency here is +1. Okay. Secondary valency is 6. Got it? Now, if I write the structure, which is pretty much similar to what I have written above, let me show you. It's very, sorry, let me rewrite that. So we have cobalt here with 6 connections, out of which 6 of them are coming from ammonia only. So all 6 are coming from ammonia. And then one is ionically bonded, which is bromine. This is bromine, which is ionically bonded. So this is how the structural representation must be as per Warner's theory. Okay. Next one, FeCl2 6NH3. So it's the same one again here also you can see Fe would have 6 ammonia and outside we have 2 chlorines. So this ratio is going to be 1 is to 2 and total Van 't Hoff factors are 3. Primary valency in this case is +2. Secondary valency is 6. The structure is pretty much the same as what we have written here, except that instead of one bromine here, we have 2 chlorines here. So which means we will have 2 connections like this. So one chlorine here and one chlorine here. So this will be the structure. And at the center, we have iron. That's it. This is the structure. Next one, nickel complex. You can see that here. Next one, we have nickel with NH3 4 times and 2 Cl2 inside and 2 Cl2 outside. Ratio is again 1 is to 2. Van 't Hoff factor is 3. Primary valence is +4. And oxidation state here is, coordination number is 6. And the structural representation is pretty much similar to what we have written it above, except instead of iron, now you will have nickel. So here we'll have nickel, okay, and 2 chlorines. Now this is an interesting part. 2 chlorines are outside, but then there are 2 chlorines are also inside. So basically these two are chlorines inside, but because they are anions, they will be a part of, I mean, they will contribute towards primary valency also. So this is how you will represent. So everybody look into these structures properly. This is a complex. This is its structural representation. Okay. Right. What are the main drawbacks of Warner's theory here? You can notice that main drawbacks. Okay. First thing is the assumption that six ligands are octahedral, six ligand complexes. Sorry, six ligand complexes are octahedral, and four ligand complexes are tetrahedral. Unfortunately, this will not remain correct, because you can always have you can always have four ligands which are not tetrahedral, which could be square planar also. They could remain square planar as well. So assuming that is not correct. Okay. Second thing, this assumption is not correct. Second thing, primary valency of every uh, every central atom is fixed, which is also not correct. Going ahead, we learn that metals may have multiple primary valencies, not necessarily one primary valency. It could show plus two also, it can show plus three also, and so on. Okay. So that is not fixed. Okay. Now, main another drawback is like it cannot explain anything about the magnetic and cannot explain, okay, magnetic properties, color properties of complexes. So these are typical drawbacks of uh, Warner's theory. Okay. The next concept is about Sidgwick's EAN rule. EAN means effective atomic number. Effective atomic number. Okay. Now, CMA is trying what exactly the Sidgwick's rule suggests, that central metal atom will always try to achieve the nearest inert gas configuration. It will always try to achieve the nearest inert gas configuration. Okay. And it can be represented as a formula that En is the atomic number Z minus the oxidation state of the central atom plus 2 times number of ligand connections. Not NL means not only ligands, it's about ligand connections. Or in short, coordination number. What is the coordination number of central atom? So, for example, if you notice this one, K3FeCN6, there are 26, I mean, the atomic number of iron is 26. The oxidation state of iron, which is primary valency, is plus 3, plus 2 times of secondary valency, which is number of ligand connections, are 6 into 6. So that makes it 35. Okay. Which is definitely close to krypton. Okay. And at the same time, now if you notice for EAN here, that will be 26 minus of plus 4, plus 2, because now this time the oxidation state of iron is plus 2, plus 2 times of 6. Now this is coming out to be 36, which is exactly same as krypton configuration. So iron is in a way making a complex to attain the same valency as a same configuration as that of krypton. Now, according to the EN rule, or according to the Sidgwick's EN rule, we can say that complex 2 is more stable than 1, stability wise. Okay. But is it always correct? No. This is going ahead, we learn that this is not actually correct. Okay. In fact, this complex is more stable than this complex. So it is kind of overwriting the Sidgwick's rule. So Sidgwick's rule, although it is a better, I mean, it is a good thought that there is a chance of octet completion. But do we define the stability just on the basis of that particular configuration? No. Okay. So this is something we will learn, right, going ahead, that why just simple EN number is not enough. Okay. But for now, one very standard J question is to figure out what is the EN value. How much is the EN value of a given complex coming? Okay. So notice this, everybody, right from scandium to radon, I have given you the atomic numbers of all the elements. Let's do it together. How to calculate the EN values, everybody. Please check one by one. First thing, whenever you have such questions, first thing you will do is figure out what is the primary valency or the oxidation state. Oxidation state of iron here is +2. Secondary valency, which is the number of ligand connections, which is +6. So that makes En value much more easier now. So that will be equal to 27, 26, which is the atomic number of iron, and oxidation state is +2. Okay, plus 2 times of number of ligands, which is 6. So you can clearly notice that the En value is 36 in this case. Next case, nickel Cl4 and 2 minus. Primary valency in this case, or oxidation state in this case, is +2. Secondary valency or number of ligands in this case is only 4. So En value will be equal to, okay, nickel, which is 28. Okay. And then oxidation state is, 2 plus 2 times of number of secondary valencies, which is 4. Okay. So that 8 and 28 minus this one is 26. 26 plus 12. Okay. So how much we have this one? 26 plus, sorry, not 12, 8. So that makes it 34. So En value is 34. So as per Sedgwick's rule, this is yet to attain stability. 2 more electrons, if it gains, it will attain stability. This is only as per Sedgwick's rule. Okay. Next, platinum. Atomic number of platinum, if you go to this, you will find out as 78. So let's do it together, everybody. Okay. So primary valency or oxidation state in this case is, +2. Check. Secondary valency or the number of ligand connections are 6. So EAN value in this case will be equal to platinum, right, which is 78, minus oxidation state 2 plus 2 times of ligand connections. So this is 76 plus 12. Okay, clear? Sorry. So you can see 12 plus this one. So we are getting it as 88. Okay. And this is greater than that of radon, which is 86, isn't it? So of course it is not very stable as per Sedgwick's rule because it is overshooting the octet value. Okay. I mean inert gas configuration value. Next one, primary valency. Notice that primary valency in this case, oxidation state here is +4. Secondary valency is 6. So now the En value here will be equal to 78 minus 4 plus 2 times of 6. So that is coming out to be 86, which is same as that of radon. Okay. Third one. If you split this, it will convert into 2K plus PT Cl6 overall 2 minus. So primary valency in this case here is plus 4. Secondary valency in this case is 6, which is number of ligands. So if you put in the formula, so En is equal to 78 minus 4 plus 2 times of 6. So 74 plus 12, so 86. Same as radon. Yeah. Try the next one. FeCO5. FeCO5 primary valency is 0, secondary valency is 5, or which is the number of ligands. So En value will be equal to 26 minus 0 plus 5 into 10, which is 36. So this is a perfect, match. So this is satisfying the nearest inert gas configuration. Palladium. Go to palladium. Palladium is 46. So primary valency in this case is plus 2. Secondary valency in this case is 4. And EAN value. So 42 minus uh, oxidation state is 2 plus secondary valence is 4 into 2. Done. So that makes it 40 plus 8. Okay, which is 48. Got it? Now, what is the nearest one, beta? Nearest one in this case will be xenon, which is 54. Okay. Sorry, palladium is 46, beta. I'm 46. So 46, which means you have to add another 2. So that makes it 52. Zinc. Check out primary valency. Primary valency here is 2. Secondary valency here is 6. Sorry, 4. En value is equal to En will be equal to atomic number of zinc, which is 30 minus um, oxidation state is 2 plus 4 times of 2. So that makes it 28 plus 8 more. Clear? So this is also satisfying the octet. I mean, inert gas configuration. Okay. Now, when it comes to metal carbonyls, although the stability based on En value is not just for all the complexes, but it is definitely valid for coordination complexes. Coordinate complexes will be the best way to look into. Check. Let's see CO6 atomic number. If you notice, this is 24 minus 0 plus 2 times of 6. So how much we have? 24 plus 12. That makes it 36. So here the coordination number is perfectly matching. See the second one. 25 minus 0 plus 2 into 6. So that makes it uh, 12. So 35. Sorry, 37 in fact. Okay, 37. So 37 is greater than 36, which makes it manganese will be ready to give away one electron always. So acts as reducing agent. Acts as reducing agent. Clear? It will act as reducing agent. Next, when it comes to vanadium, so 23 minus 0 plus 2 times of 6. So what do we get? So that is 35, which is less than 36. So that makes it to act as oxidizing agent. Oxidizing agent. Okay. So when it comes to MnCO6, it will be ready to lose one electron and convert itself into plus and give one electron like this. Next, VCO6. It will be ready to accept an electron and convert itself into VCO6 overall minus. Okay. This is the way it will operate. Okay. So remember guys, especially if you have metal complexes, make sure you notice whether they can act as reducing agent or not, they oxidizing and reducing agent or not, simply on the basis of En number. If the En number is 36, that means no problem, it is stable. If it is 37, 35 like that, that means it is unstable. It will be ready to either lose electrons or gain electrons. Got it? That's one good advantage of En values. Everybody clear on this part? Please notice quickly once. If you have written all of them, then we can go ahead. Okay. Now, everybody, let's look into the next theory, which is valence bond theory. Got it? Of course, I told you like Sedgwick's rule, the main drawbacks are being, not validated for all the complexes. It's fair enough for only metal complexes. Now, when it comes to valence bond theory, what are all the factors we need to notice? First, valence bond theory mainly help us understand what is the hybridization of central metal atom. Okay. And unlike chemical bonding, where we make hybridized orbitals using unpaired electrons, right? We use the orbitals having unpaired electrons, we mix them up, and then we make a covalent bonding with the other compounds. But here it's not the case. Here metals will use the empty orbitals. Okay, they will use empty orbitals to make a hybridized orbital. And in those empty orbitals, ligand will make coordinate covalent bonds. And that's the way we will get the uh, that's the way to figure out what is the hybridization of the central metal atom. Second, ligands carrying lone pair will be the one to overlap the empty hybridized orbitals, which is to form forms coordinate covalent bonds. Okay. Other than that, the next important aspect we need to understand is what are the type of hybridizations. If we may could recall from from chemical bonding, types of hybridizations involved. Hybridizations involved. Check out. If an empty s orbital and an empty p orbital, if they mix, you will get this as sp, and the shape would be linear. Second, if you have s, p and p, two p orbitals are mixed. It could be px, py, px, pz, anything. It will become sp2, and that will remain trigonal planar. Trigonal planar. That is the geometry of the hybridized orbitals. Next, if you have s and px, py, pz, all of them are mixed together, then we shall get this as sp3 hybridized orbital, and it will look tetrahedral. So that will form tetrahedral geometry. Now is the interesting cases. These are very regular cases which we are aware of. Now notice that what if you have S, P, X, P, Y, P, Z, and then D, Z square we have. Then we will have this as SP3D, and that will also form trigonal bipyramidal. Trigonal bipyramidal. Okay. Next one, in case if you have s, n minus 1 d, that means inner dz square, that can also be mixed with ns and np3, all p3 orbitals, to get the hybridization of dsp3. So instead of sp3d, it could be dsp3, and that will also still remain triagonal bipyramidal. Sorry, triagonal bipyramidal, right? Bipyramidal. Another one which you will notice is n minus 1 d orbital. Which d orbital? That has to be very specific here. That is x square minus y square. That has to be mixed with s, then px and py. Only mixing of these orbitals will give you, 1 minute, let me rewrite. It has to be ns plus npx and npy. Mixing these, you will get the hybridized orbital as dsp2, and dsp2 is square planar. This is going to be square planar geometry. And next one we have n minus 1d, okay, n minus 1d, x square minus y square plus n minus 1d z square plus ns plus np3, all three orbitals. If you mix it, we will get this as d2 sp3. Okay, d2 sp3. d2 sp3 is going to be octahedral geometry. Same thing I can do it the other way around. That is ns np3, and then we have nd x square minus y square plus nd z square. Putting all that together, we'll get this as sp3d2, which will also be an octahedral geometry. These are the main, mixing of orbitals which you will notice, and forms various various geometries here. Okay. So starting from sp, sp2, sp3, sp3d, dsp3, dsp2, d2sp3, and sp3d2. These are the hybridized orbitals we will look into. So be very specific about which orbitals we are mixing in all these cases. Okay. Now, one important note here is, now if n minus 1 d orbital is used for hybridization, then we call complexes as inner orbital complexes. Inner orbital complexes. For example, if a complex is formed using dsp3, dsp2, d2sp3, then we call all these three as inner octahedral complex. These are called as inner octahedral complex, everybody. And in case if you are using nd only, okay, so that is nd orbital is used, then it is called as outer orbital complex. Inner and outer orbital complex. So please check this out and differentiate it. Okay. Now, there is one brute assumption here when it comes to valence bond theory, that nature of ligands, nature of ligands, okay, can be distributed into two types. One is weak field ligand, which means weak field ligand, are the ones which does not have sufficient energy, does not have sufficient energy to pair the inner electrons, to pair the inner electrons of central metal atom. Okay. And it is regarded that, you know, oxygen and halogen based, oxygen, halogen and sulfur based ligands are generally generally weak field ligand. WFL means weak field ligand. Okay, keep that in mind. Next, when it comes to strong field ligand, which means it have sufficient energy to pair the inner electrons of central metal atom. Okay, and generally nitrogen based, phosphorus based and carbon based ligands are strong field ligands. Okay, last thing, priority of hybridization. Got it? So DsP2 is always more preferred compared to sp3. Okay, if n minus 1d empty orbital is available, empty orbital is available, then this orbital is more prioritized. Similarly, D2sp3 is more prioritized than sp3d2 if n minus 1 d2 orbitals, empty orbitals, empty orbitals are available. Okay, so these are some basic fundamentals we need to learn from VBT theory. Got it? Now, if you notice the list of the ligands, the ones which are oxygen, sulfur, and halogen based connections which form weak field ligand includes chlorine, iodine, fluorine, bromine, hydroxide, water, oxalate, sulfide, oxide, peroxide. These are all oxygen connected, sulfur connected, or halogen connected ligands. While NPC connected ligands, if you compare nitrogen, ethylene diamine, pyridine, triphenyl phosphine, PR3, cyanide, carbon connected, C2H4, carbon here, carbon, nitrogen, nitrogen connected. So these are all going to be strong field ligands. Okay. So quickly go through the VBT ones, everybody. Just give a quick reading, then I will take you through problem solvings. Okay, I'll give you a minute. Please go through it quickly. Now make sure everybody is aware of the list, because list is something which will help us understand whether it is weak field or a strong field. Got it? Suppose if I were to find out the hybridization of central atom in this complex and in this complex, how do we do that? Okay. So what we typically do is, like, you put it like an algorithm, everybody. Okay. So what is that algorithm? Let me show. Okay. So here, first, in the first case, you always identify what is the primary valency. So the primary valency in this case is +3. Secondary valency in this case is 6. Okay. Same is the case here. Primary valency is +3. Secondary valency is 6. Okay. Now, next thing is write the configuration of iron. Iron is 26. Atomic number iron is 26. So we have argon 4s2 and 3d6, and we know that 4p is 0, 4d is also 0. They are available, but they are empty. Same as the configuration goes for here also. This is the general configuration. Now, because it is +3 oxidation state now, okay, because it is +3 oxidation state, okay, so what we can say, now iron has become +3 oxidation state. So since it is becoming +3 oxidation state, The electrons will go from 4s and 3d. So 4s will be the first electrons, then 3d one electron will go. So here also we'll have 4s 0 and 3d 5. This is the configuration after getting plus 3 oxidation state. Now is the interesting fact from here onwards. Now cyanide is approaching. As cyanide is approaching, it is a strong field ligand. Here chlorine is approaching, which is a weak field ligand. Okay. And what will cyanide do? Cyanide will try to notice that there are six cyanides I can accommodate because six cyanides are coming. So six cyanides are to be accommodated. For six cyanides to accommodate, there are only two type of hybridization. So that is D2sp3 and sp3d2. Only these two are the hybridization available. D2 means inner d orbitals. Here sp3d2 means outer d orbitals. Okay. Now, in such case, we can say that if it is about inner d orbitals, correct, which means I should be having 3d x square minus y square and 3d z square free and mean empty, then we have 4s and all 4p3. So 4p is anyway empty. 3d can I make into two orbitals which are empty here? Yes, we can. How can we make it? See, because in this case of 3D, you will notice that uh, 5 electrons are present. So now let me write it in terms of blocks. So this is block of 5 orbitals. 1, 2, 3, 4, 5. This is 3D. Then we have 4s. Then we have 4p. Okay. So in 3D, we have 5 electrons. So that makes it 1, 2, 3, 4, 5. Now check this out that there are all six empty orbitals are open up. And these empty orbitals will mix together to form D2sp3 hybridization. But when it comes to Cl minus, again the logic is same here. So they could have gone for either sp3d or D2sp3. But since chlorine is a weak field ligand, it will not have the strength to pair these electrons. Hence, we do not have any other case but to make sure 4s orbital which is empty, 4p orbital which is also empty, 4d orbital which is also empty. These are the orbitals we can use. 3d cannot be used. 3d will remain as 3d 5 only. So these are the orbitals which can be used, right? And that will make it as sp3d2. So we will get this as sp3d2 hybridization. So one will become D2sp3, other will become sp3d2 hybridization. Okay. Now in D2sp3, what is happened after the pairing? Count the number of unpaired electrons before and after. Initially, when you have 3d5, number of unpaired electrons are 5. Here also, number of unpaired electrons are 5. But after the formation of the hybridized orbital, now the number of unpaired electrons are only 1. Now here the number of unpaired electrons are 5. They remain 5 because in 3D 5 the electrons are the same. We are not disturb them. So it will remain those same 5 electrons. Now notice this one. If number of unpaired electrons decrease after ligand has approached, then complex is low spin based, low spin complex. We call it as low spin complex. While if number of unpaired electrons remain same, okay, then it is high spin complex. then it is called as high spin complex. Okay. So using this fundamental, I can say that, okay. So if you compare that, we can definitely say here, this one is being low spin complex and this one is being high spin complex, high spin complex. Okay. Next important part, you know, what type of octahedral geometry that you are getting here? What we are getting here is an inner orbital. Okay. Inner orbital complex. Inner orbital octahedral complex. Octahedral. While here, in this case, it is outer orbital because it is using the outer d orbitals, 4d orbital. Outer d octahedral complex. Lastly, because the number of unpaired electrons are greater than 0, so this will remain paramagnetic. This is a paramagnetic complex. Here, number of unpaired electrons is 5, so which is still greater than 0, so that remains paramagnetic. So the only property which is very similar is paramagnetic nature. That's all. Other than that, all other factors are different. So this is the algorithm. You need to solve it for every question, everybody. For every complex, you should know how the distribution of electrons are, how to identify whether it is low spin or a high spin, how to mark it as an inner or outer orbital complex, whether it is paramagnetic or not. Okay. And what is the final hybridization, whether it is D2sp3 or sp3d2 if it is 6-membered ligands. Please check. Please do ask if you have any doubt. Right, let's do the next one here. Next one, we have basically chromium plus 3 here. So chromium plus 3 here and chromium plus 3 here. Got it? So here, notice the oxidation state is clear. So this is plus 3 oxidation state, plus 3 oxidation state, and plus 3 oxidation state. Okay. So we'll follow the same algorithm, everybody. Start working along with me. Primary valency is 3, secondary valency is 6. Same logic here also. Primary valency is 3, secondary valency is 6. Primary valency is 3, secondary valency is 6. Okay, next. Nature of the ligand. So if you notice the nature of the ligand, water is a weak field ligand, ammonia is a strong field ligand, cyanide is a strong field ligand. Got it? Next, configuration. So if you notice the chromium configuration, chromium would be usually argon 4s1 and 3d5. And this configuration is same initially before ligands approach. It is the same for all three cases. Next, as the ligand approach here, so this is a weak field ligand, sorry, first coordination oxidation state. So if you notice here also chromium plus 3 is present, here also chromium plus 3 is present, here also chromium plus 3 is present. So which makes it this as argon 4s0 and 3d3. 3d3. So if it is configuration wise, it is the same in all three cases. Okay, next. As the weak field ligand approaches, we cannot do any pairing. But notice something very interesting here. So when it comes to 3D here, correct? In the case of 3D, we have 5 orbitals, then we have 4s, then we have 4p, correct? So this is 4s, 4p, and 3D. In the case of 3D, how many orbitals we have here? So total 3. So 1, 2, 3. So 3 orbitals we have. Got it? Now, what is the hybridization we have here? Check out. We have this as D2sp3 possible. I mean, without pairing of electrons also it is possible. Correct. So, is there any necessity for pairing? Not needed here. In fact, weak field ligand cannot do it. Just because it can't do, does it mean we have to take higher orbitals? No. As long as the inner orbitals are available, we'll always use the inner orbitals first. So D2sp3 is more preferable than sp3d2 for the fact that D outer d orbital will always have more energy carried. So this will have more energy while this will have less energy. So orbitals will less energy orbitals are always utilized first. So therefore D2sp3 hybridization will be observed. Now here also it is the same case because irrespective of whether you have a strong field ligand or a weak field ligand, here we have a strong field ligand, here also we have a strong field ligand, but it does not make any difference because configuration, I mean, since it is D3 configuration, for D3 configuration, whether it is a strong or weak field, you will always have the same configuration. So now since number of unpaired electrons are 3 in all the cases, number of unpaired electrons, if you notice, it is 3 here and 3 here. Initially also when the number of unpaired electrons were checked, it is number of unpaired electrons as 3. Here also it is 3 and here also number of unpaired electrons are 3. Got it? So number of unpaired electrons are not changing everybody, right? So in that case, since the number of unpaired electrons remain the same, do we call it as high spin? No. Reason being, if electron configuration cannot cannot differentiate, okay, strong field ligand and weak field ligand, okay, then that's awesome. Thank you. You're welcome. Okay. Right. So if you cannot differentiate strong field, weak field ligand, then if electron configuration cannot differentiate strong field or weak field ligand, then high spin or low spin is not defined. High or low spin is not defined. So high spin and low spin are only subject to the differentiation of strong field and weak field. See here, whether you take water, whether you take ammonia, whether you take cyanide, water, ammonia, cyanide. So it does not make any difference as long as it is D3 electron configuration, right? Hence, we do not use the terminology high spin or low spin anymore. Instead, we definitely know that all three are using inner d orbital. So it is an inner orbital octahedral complex. Octahedral complex. Okay. So that is the same in all three cases. Okay. And next, another important part is in all these cases, it is paramagnetic only because it has unpaired electrons. Paramagnetic. So here also paramagnetic, paramagnetic, and paramagnetic. So paramagnetic nature is not changing. So this is how it would be. Everybody, please look into it. If you have a doubt, you can ask me now. First, let me change this two complexes. Let me rewrite that. Second. Let me rewrite these two complexes. One is nickel NH3 6 times plus 2. The other one is nickel En thrice plus 2. Okay. Check these three cases now. In all these three cases, uh, configuration wise, primary valency wise, everything is same again. Okay. It's very similar to what we have done earlier. So primary valency is 2, secondary valency is 6, And that's the same thing in all these three cases. Okay, next, electronic configuration. Electronic configuration. So you see, nickel, plus 2. I'm directly writing plus 2 now. Plus 2 configuration is argon 4s0 3d8. The same configuration follows here also, right? And then we had an approach of weak field ligand. Here we have an approach of strong field ligand. Ethylene diamine is also a strong field. So because of nitrogen connections, it is also strong field ligand. Next, if you notice, because of weak field ligand, would you be able to make any pairing? Right. See, since it is a weak field ligand, we will not be able to pair anything. So 3D will remain the same. So let me write down first the 3D orbitals. So this is 3D orbitals 1, 2, 3, 4, 5. Then we have 4s orbital. Then we have 4p orbital. And last we have 4d orbital 1, 2, 3, 4, 5. Okay. Notice the number of electrons here, guys. So we have 6, 7, 8. So this is 3D, 4s, 4p, 4d. So this is the original configuration. Okay. So the same should have been in the other cases. But now is the interesting part. Now, in these cases, in weak field ligand, I can't do anything. So I have to rely only on the outer d orbital. Hence, hybridization will become sp3d2. But when it comes to inner d orbital, when it comes to these orbitals, we can make sure that this electron can pair here because other three are anyway in the paired form. What if I pair this one also? In case if at all I pair it, so is there any use or not is what you need to check. So imagine if at all I paired it. Okay. So on pairing it, I would be getting the 1d orbital open like this. So, but that is not enough because one inner d, one outer d is not how we make a hybridization. It always has to be either two inner d or it has to be two outer d orbitals. Got it? So it cannot be like one inner d and one outer d orbital. Okay, clear. So hence, what we can do, what we can say here is that since this hybridization is not possible even after pairing, so it is not useful to pair it. Okay, so we should never pair electrons, correct, unless we have the use of it. Got it? So pairing here is not helping. So despite having a strong field ligand, the pairing does not take place in this case. So let me just simply write it this way. So no pairing here. So since there is no pairing here, so what we can say, here you can notice that this will also utilize sp3d2. This will also utilize sp3d2. So hybridization in all these cases would be same. And since you are not able to make any difference between a strong field and a weak field ligand, this concept will be again valid. So we cannot say it is high spin or a low spin complex. So none of them being neither high spin nor low spin. Neither high nor low spin complex. Okay. Hybridization is the same. So since you are using an outer orbital, so we can say this is an outer orbital, outer orbital octahedral complex. And all of them will remain paramagnetic because number of unpaired electrons are 3 and that is the same in all three cases. So please look into it, everybody. Done, everyone? Right. Okay, guys. So next are all the exceptional cases and four ligand system. So this will continue in the next class.